All right, and we're going to look at section 1.5, which is parent functions and transformations. So this is something that you have seen in Algebra 1 and Algebra 2. It's basically what the graphs, the different functions look like. So, and parent functions are like the most basic of each group of functions. Okay, where you're not adding or subtracting anything to it or multiplying anything to it. Yeah, those are parent functions, the most basic. And we're going to look at a few of them. The objective today is you'll be able to identify a graph and describe parent functions. So the first one that we always start off with is the constant function. The constant function is yeah, just a line. So it's f of x equals c. It's a horizontal line. It is wherever the whatever that c is. So for example, if the c is 2, then it is f of x equals 2. It's just going to be a horizontal line at y equals 2. And that's it. All right, so that is the parent function for that. And now when c equals 0, f of x is the 0 function. So if c is 0, that's a bad line. This here, then we have the 0 function. All right, and then we have the identity function. Identity function is that's where y equals x. Remember, so they each equal each other. So whatever happens to the x, the same thing happens to the y. So here, um, that is basically this. It looks like this linear function. That's basically what it is. Y equals x. Up one to the right one, up one to the right one. And that's it. And then we have the quadratic function. So quadratic, remember, that's where we have um, our um, our exponent is 2. So the main power is 2 there. So x squared. Okay, and our cubic function is where our biggest exponent is 3. And yeah, that's what that looks like. So for the quadratic, we have a parabola. For the cubic function, we have that uh, little uh, parabola that's going in one direction, I guess. All right, let's put those on the notes because those are good to know. All right. And now we're going to look at the square root function. So the square root function, it looks like a sideways, looks like a sideways parabola, but cut in half, right? Which is basically what it is. Um, and the reason why it's cut in half is because uh, you can't have negatives inside of, uh, sorry, so this is always going to be positive, right? And we can't have negative x's, so there's nothing over here on the left side. So there you go, that's it. It's a square root function. And the reciprocal function, and notice it looks like 2 hyperbolas. So yeah, 1 over x, f of x equals 1 over x. That's what it looks like. That's the reciprocal function. Now we'll see some more detailed ones later. We'll know them as rational functions. And then we have absolute value functions. Absolute value functions, we have that v, the value, right? And the reason why is because whenever we have a negative, it turns positive. So you're always going to have a positive y there. Okay. And we'll look at translating these, transforming them um, in the next section, or it might be in the later section. I think it's the second half of the section. All right, so you have that one, absolute values. Now this one's a little different. I don't think I'm not sure if you've ever seen this one. If you've seen it, cool. If not, no worries. You don't really see it too often. And you might see it in business though. So if you do go into business, this is called a step function. Why? Because it looks like stairs, right? Looks like stairs there. So that's a step function. And this it says the most well-known step function is the greatest integer function. So the greatest integer function, it looks like brackets, but double-lined brackets. Okay. So for example, if we had any number, oh, what it means is if you have any number, let's say 0.7, it's going to be the greatest integer less than or equal to x. Okay, so anywhere from, so if you look at a number line, so 0.7, I'm just kidding. Oh, here you go, 0, 0.7, and okay, at 0.7, the greatest integer is the one that's to the left of it, which is 0. So this one would be 0. And if we had 2.7, 2.7. All right, the greatest integer, so go to the left, we have 2. And then if you have a negative, -2, -3, if you have negative 2.7, right, negative 2.7, again, the integer to the left of that is -3. So that one is a little tricky when you have those negatives, okay, because it looks like it's bigger, but it's actually less. Okay, so basically you're rounding it to the nearest, um, to the biggest integer. Okay. For an integer smaller than or equal to that. Okay, so if it's 2, then it would still be 2. So if it is an integer, then it stays that integer. All right, and that's that. So let's look at this one. Oh, so for example, at 0.5, the greatest integer of 0.5 is 0, so it stays 0. All right, and when you get to 1, you get 1, but 1.1 is still 1, 1.2 is 1, 1.3 is 1, 1.4 1, etc., 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 up until 1, and up until 2. 2, it's 2. 2.1, 2.2, 2.3, 2.4, 2.5, 2.6, 2.7, 2.8, 2.9, and 3 up here. 3.1, 3.2, 3.4, 3.5, I can't speak that fast. Okay. All right, so there you go. That's why it looks like that. And notice that we have those open circles at each of those because we want to say that it gets really close. It gets to 3.999999999 is still 3, but as soon as you get to that 4, then it's goes to 4. So that open circle tells us that it's really, really close. Okay, really, really close to 4. And there you go. So you're going to see these a lot. In this section, we will see it, but later on, not too much. And again, you'll see this in business classes. Put on my notes. So that's the greatest integer function. All right, so we want to describe the parent function. All right. So here it says describe the following characteristics of the graph of each parent function: domain, range, intercepts, symmetry, continuity, and behavior and intervals on which the graph is increasing or decreasing. Okay. So yeah, they're all going to be different. If you want to, you can just look at the graphs there. Here, I'll do 2. If you want to try 3. All right, I'll do 2 here. So for this one, if you want, you could just go back. Oh, let's do the domain and range first. All right, so let's look at that function. That's the reciprocal function. 1 over f of x equals 1 over x. So what's our domain there? The farthest left, it goes all the way to negative infinity. And then it goes, is there anywhere that it doesn't, where it's not possible in the x coordinate? Yeah, right there at 0. Notice that there's that invisible line there. Okay. So from negative infinity to 0, and then back to 0, all the way to positive infinity. Okay. All right. So that's our domain and our range. Let's put our domain here. Goes from negative infinity to 0, and then from 0 to positive infinity. Oh, why they do that? Does it say divide it in? Okay. They put it in set builder notation, but I'm going to put it in set interval notation because it's easier. Uh, okay, but if you want, they wrote it like this. The set of x where x is not equal to 0 and x is an element of real numbers. All right, so you can look at it either do those do either of those ways, and then we have the range. So the range is the lowest. So the lowest that it goes is negative infinity. And then for this one, it goes all the way up to and then approaches 0 again. It goes to 0. Then we also have a break there, and then it goes from 0 to all the way to the top, positive infinity. All right, and again, it would be the same for the set builder notation. And then what else do we have to do? We have to find domain, range, intercepts. Okay, intercepts are the x and y intercept. Is it crossing the x-axis? None. Okay. So x-intercepts does not exist. Y-intercepts does not exist because it's not crossing the x-axis and it's not crossing the y-axis. And it never will because we have asymptotes there. All right, and then we have symmetry. All right, so remember symmetry, it's either going to be symmetrical about the x-axis, so that it would be where the top and the bottom look the same. Okay, that's what it would look like, but it doesn't. Symmetric about the in y-axis would be the left and right would look the same. That is not what it looks like either. Here, the last one we have is the symmetric about the origin. Okay, and this one is symmetric about the origin because if you flip it upside down, so you can look at it upside down, you'll get the same shape. So this one goes here, this one goes down there. It lines up nicely. So symmetric about the origin. And then the next thing is continuity. So continuity, is it continuous everywhere? So, and then it stops, right? It doesn't stop, but it keeps going, and then it continues over here. So notice that there's a discontinuity at x equals 0. So there's and what kind of discontinuity is it? It's an infinite discontinuity. Because on the left side of 0, it's going to negative infinity. On the right side of 0, it's going to positive infinity. All right. Remember, we have 3 different kinds. We have the whole, right? We have the jump, and we have the infinite discontinuity. So those are the 3 different kinds: the whole, jump, and infinite discontinuity. So infinite discontinuity at x equals 0. And what next? There's a lot. End behavior. Okay. So on the left side, so as oh, I put limit. Okay, that's fine. Um, so here's domain and range, intercepts, symmetry, continuity, and what did I say this one was? End behavior. Okay, so end behavior is what's it doing as it goes to the left forever. So we can write that as f of x approaches And here, notice that it's approaching 0 on the left side as you go left. So f of x approaches 0 as x approaches negative infinity, as x goes to the left. Or you can write it as the limit of f of x as x approaches negative infinity is 0. Either way works. Left. All right, and then you can also write f of x approaches 0 also as it goes to the right, as x approaches positive infinity. So you can also write that as limit of f of x as x approaches positive infinity equals 0. All right, so we have domain and range, intercepts, symmetry, continuity, and behavior. There's more intervals on which the graph is increasing and decreasing. Last one, okay. So remember, for increasing and decreasing, you want to start on the very left. Right? Imagine you're walking and on the graph, what are you doing? As you go to the right, you're going down. Okay, so it is decreasing from negative infinity all the way to 0. And these are x values, remember, x values. So from negative infinity all the way to 0, you're decreasing. And then let's skip over here. So here you are, yay. And you go to the right, you're still decreasing. So from 0 to positive infinity, you're decreasing, and that's it. There's no increasing here, okay? You're not going up. It's just going down, and that's it. All right, put this there. And I think that's it for today. Yeah, and tomorrow we'll look at transformations, translations, right, reflection, rotation, dilation. Okay, so reflections, translation, and things that you've seen before. Um, you might need to see them again. That's okay. Yeah, it's always good to see stuff over. So let's look at that tomorrow. All right.